Hello again. So for this lesson, I'm more just going through a quick survey of a bunch of different functions, the vast majority of which you are already familiar with, at least to some extent. And so first, let's start with linear functions. Quite straightforward, but incredibly important. And so, like it says here, linear functions are often expressed in the form mx plus b, where, as I'm sure we know, m represents the slope and b is the y-intercept. However, that's what we call slope-intercept form. There's countless ways I could express a linear equation. Another way that's quite helpful is what we call in point-slope form, in which you have the slope times x minus y1 plus y1, in which case in this form, x1 and y1 represent some point on a line. So they represent the coordinates, the ordered pair of just some point on the line. And so that form there, m times x minus x1 plus y1, and there's other variations of that, is what we call slope point form, which tends to be quite helpful. That said, if I just look at these two examples of linear functions, the one on the left is in slope-intercept form. And again, there's your slope, there's your y-intercept. I'm pretty sure you know all this already. But that said, it is so important, it's worth me saying one more time. Just because something is relatively straightforward doesn't mean it's not extremely important. And then for my other example, which is in slope point form, there's a slope 1/2, but this minus 3 and plus 2 tell me that not only does this line have a slope of 1/2, it tells me as well, I know this line also goes through the point positive 3 comma positive 2. All right, so expect to see linear functions throughout this course. It is actually leads to one of the fundamental ideas of calculus, but I don't think I need to linger on that more. So next I want to talk about polynomial functions, which includes linear functions and quadratic and cubic functions. They're often written in this form where we have x, some coefficient times x to the power of n, where n must be a whole number. And that's what we call the degree of the polynomial, the biggest power on x, but it has to be a whole number. It can't be an integer, it can't be a negative integer, and it can't be a rational number of like a decimal or non-whole number. And in general, since polynomials all have a degree that starts at 1, or actually starts at 0, and goes up, they're always generally positive, even or odd degree. And so if it's an odd degree polynomial, the end behavior is in quadrants 3 and quadrant 1, or quadrant 2 and quadrant 4. And if it's an even degreed, it's quadrant 2 and quadrant 1, the end behavior, or quadrant 3 and quadrant 4. That's it. Huge variety of polynomial functions. Here's 3. And so first, f of x is a quadratic polynomial. So it's degree 2. Because the biggest power on x is a 2. And again, this is an example of a quadratic, which is a type of polynomial. And the end behavior of this is going to be quadrants 2 and quadrant 1. For example, I can visualize parabola is going to be opening up. It looks like this. The phrase opens up only makes sense for certain types of polynomials. It doesn't make sense for a polynomial like this. This opens up and down. So that's why we don't use the phrase generally opens up for polynomials in general. But if I look at this particular parabola, in the end it's going up to quadrants 2 and quadrants 1 forever. So end behavior, quadrant 2 to quadrant 1, or vice versa. Okay, this next one is a cubic polynomial of degree 3. And if there was no negative coefficient in the front, this would have end behavior in quadrants 1 and 3. But there's a negative in the front, so I have to imagine this being reflected vertically compared to the graph of x cubed. And so this is going to have n behavior in quadrants 2 and 4. This particular cubic function is going to look something like that. In quadrant 2, quadrant 4. Lastly, I have x to the power of 10. That is a 10th degree polynomial. And I'm sure someone's come up with a fancy Latin name for it, but I'm just going to go with degree 10. I don't really care. Honestly, you should know that a linear is degree 1, quadratic is degree 2, cubic is degree 3. After that, I don't really care. This function, though, even though I don't know the exact name for this particular degree, I know the n behavior. And that's because it's an even degree with a positive leading coefficient. So I know the n behavior of this function is going to go from quadrant 2 to quadrant 1. Or vice versa. All right, next, and what is probably new, although we've dealt with these, just the phrase is kind of new, is what we call a power function. And a power function is any function in the form x to the power of a, where a is any constant real number. Okay, so it's still a constant. It's not a variable. So this is not an exponential function. The variable is the base. But a doesn't have to be a whole number, which is like a polynomial. And that's what kind of differentiates this from a polynomial. However, as it says for this first point, if a is a whole number, then this is also an example of a polynomial. If a is greater than 0, but not a whole number, like a half or 2/3 or 3/2, it can always be expressed as a radical. If x is less than 0, sorry, if a is less than 0, if you have a negative power, then it can always be expressed in the form 1 over x to the negative a. Right, now I want us to be clear about something here. If a is negative, so let's say it's negative 2, then you can express it as 1 over x to the negative 2, which means positive 2, right? Negative of a negative number is positive. And that's what it says there in brackets, where negative a is actually a positive value. And again, let's look at some examples of these. None of this is new. The only thing that's new, I guess, is the phrase power functions, but all these other ideas are not new. So x to the 1/2, that's a power function. But also the power is greater than 0, and it's not a whole number, so I can express this as a radical, in this case, root x. Right, they're totally equivalent. One's not better than the other. Next one, g of x. X is to the power of -1. So this is an example of where I can express it if I want as 1 over x to the negative -1. Now, I'm going to change that. That's not wrong, but negative -1 is the same as positive 1. Or just 1 over x. And x to the 1/3, I can express as the cube root of x. So if you look at my examples up here, hopefully these last 2 points are fairly clear now. For example, if a is positive but not a whole number, these are like 2 examples of those. And if a is negative, that's an example of how I can write it. Just keep in mind before I move on, please don't think any of these other forms of these functions that I've written down are somehow considered to be simpler. They're just equivalent, and that's what's important, to know that they're equivalent. All right, rational functions. Again, going back to pre-calc 12. They're often expressed in the form g of x over h of x, where each of these are polynomials. They don't have to be expressed in this form, but if it is a rational function, there always is a way to express it in the form of one polynomial divided by another. And quite often they have discontinuities. And discontinuities will always occur whenever you're dividing by 0. So whenever h of x equals 0. And so for example, right here, if I look at f of x, I can see that when x is -2, I'm going to be dividing by 0. So I know there's a vertical asymptote at -2. If I look at g of x, I can see right here that when x is 2, positive 2, there's going to be a discontinuity, but it won't be a vertical asymptote. And how do I know it won't be a vertical asymptote? Well, let me factor the numerator, which is the difference of squares. Okay? And now notice I have a common factor of x minus 2 that I can cancel out. So I can rewrite g of x as just x plus 4 over 1, or just x plus 4. However, we can't deny the fact that if I look at function g, the equation I gave you, I don't care what it's simplified to. If x is 2, I'm dividing by 0, and division by 0 is undefined. So that means if when I get to this point where I've simplified it down to x plus 4, I still got to realize that I don't care that x plus 4 is so simple. X can still not equal 2. Because really, what I'm writing down here should be a simplified form of this equation here. And again, if I look at this equation here, it should be pretty clear that if x equals 2, I'm dividing by 0. I don't care what the numerator is. I can't divide by 0. And so I need to state this restriction. And again, this all goes back to pre-calc 11 and 12, actually. And so because I knew from the start I had a restriction where x could not equal 2, but that factor actually canceled out, I know that this is actually not a vertical asymptote at 2. There's a point of discontinuity. Well, let's make my writing a little bit nicer. At x equals 2. Now I will say I could find, a point of discontinuity has a y coordinate, which I could find quite easily by putting the x back into the simplified expression. So it would be 6. So I know this point of discontinuity would be at 2, 6. That said, the x value is the most important part. And as well, before I move on, this phrase point of discontinuity can also be called what we call a removable discontinuity, and we'll see that later on in the course. But for now, I'll stick with the terminology you're probably familiar with. All right, next, and is it lastly? Yeah, lastly, before a final problem, trigonometric functions. Okay, there are 3 primary trigonometric functions and 3 reciprocal trigonometric functions. Sine, cosine, tangent being the 3 primary ones. First, let's look at sine and cosine. Both sine and cosine have a domain of all real numbers and a range from -1 to +1. I'll use that interval notation. Whereas tan x has a domain that's not all real numbers. Tan x has a domain where x cannot be pi over 2 plus any multiple of pi, n being any integer. And tan x has a range of all real numbers. Again, tangent, sine, cosine are all related to one another. Hopefully you've learned about various identities that algebraically connect all these things together. But the way tangent behaves is distinctly different from sine and cosine. And the way sine and cosine behave is distinctly similar to one another. That's it. All trigonometric functions are periodic. That means they repeat over and over and over. The sinusoidal functions, which are functions that make waves, so sine and cosine, have an amplitude. But a tangent function does not have an amplitude. So that's it. Let's look at my 3 basic trigonometric functions. Let's sketch sine x. Sine x starts at 0, goes up and down like this, and so on. That's it. A few details I want to place on here. It goes up to 1, goes down to -1. Has x-intercepts at pi, 2 pi, 3 pi, and so on. My very quick little sketch of sine function. Cosine is congruent to this shape, but it's not the same wave, but it's congruent. And so cosine starts at 1, and then goes up and down like this, and so on. Its x-intercepts are at pi over 2 and 3 pi over 2, and so on. And still reaches, this is at 1, this is at -1. And lastly, tangent. Tangent behaves something like this, but it repeats over and over again, and there's asymptotes, vertical asymptotes. But it's still periodic, it still repeats, but it's definitely not a wave. And so for this, I want to label where the x-intercepts are at 0, at pi, 2 pi, but also these vertical asymptotes are at, this is at pi over 2, this is at negative pi over 2, the next one would be at 3 pi over 2, and so on. Now, we went into way more detail than that, dealing with trigonometric functions in pre-calc 12. That's just a quick review. So lastly, I want to come back to some actual data involving a linear model. And what we see here, this table here, this is some actual data for my nephew's height over a number of years. My brother, who is an engineer, he actually has a PhD in engineering. He's a bit of a quirky fellow, and like a lot of parents, he's kept track of his kids' heights over the years. That's pretty common, but he keeps track of his on a spreadsheet with excessive detail. But it was handy for me because I have all this easy data to access. So what I have here is some of the data. Okay, this is all we need. So, you know, various ages of this boy and his height at those times. So I want to create two models of this. One as a regression model, a linear regression model, and one linear model just by looking at the first and last points of data. First, let's look at the regression model. So what I need to do first is put this information into Desmos or some sort of technology. I'll always use Desmos. And so if I go to Desmos, there it is. So this table right here is the same information. X is the age, Y is the height in centimeters, and these are the points. Notice that this person's growing at a pretty linear manner, at least from the ages of 3.5-ish to 10.5-ish. And so to create a regression model of this, you can see down here on the left-hand side, I typed in y1 is approximately equal to a times x1 plus b, and then it created all these parameters for me. And so the equation, the linear model, linear regression model, is going to be y equals 6.57-ish times x plus 81.46-ish. All right, and the model, if I turn on the graph, looks like this. And again, that's the linear model. No model is perfect, but it's definitely pretty good, at least in the range of the data that we've been given. So let me write down that equation. So the regression model was y equals, and I'll round these values a bit, 6.57x plus 81.5. All right, so I want to now come up with a linear model just by focusing on the first and last points of data. And basically what I'm doing is I'm looking at this data, I'm focusing on this point here and this point here, and kind of imagining a line going through them, which I can just see should be a pretty good model as well. So how do I do that? Well, first I need to figure out the slope between those 2 points. And so the slope between those 2 points will be the change in y, so 151 minus 103 divided by the change in x. Which, if I decimalize that, I get about 6.67. That's my slope. Which, notice, my regression model, the slope was 6.57. So it's pretty similar. Pretty small difference, actually. And so now, to find the equation, I'm going to use point slope form. I'm going to use this form, m times x minus x1 plus y1. I got my slope. My x1, y1, I just got to pick a point. I could pick any of these. Well, I should really just pick either the first point or the last point, because that's what I'm kind of focusing on. I'll pick the first point just because it's first. And so my equation would be y equals 6.67 times x minus 3.4 plus 103. Now, again, I could distribute this and collect like terms, but who cares? I don't really care. So I'm going to leave it like that. Okay, so let me graph this and see how these two compare visually. So I'll leave that on, and here's the graph of, here's the equation of the linear model I just made. If I turn that on in red, notice they're pretty good. I mean, really, for this data, my simple linear model by just looking at the first and last points of data was pretty much almost the same as my regression model that required, a fair amount of technology to create. So I got two very, very similar models. So next, I want to use each of these models to predict the height of the boy on his 13th birthday and see what the sort of difference is. So what I could do quite easily, if for each of these models, I could just replace x with 13 and substitute that in. And I could algebraically go back to each of my two models and substitute x with 13. And I know I should get a pretty similar value for each. Or if I already have this out, and I like visuals, I'll just draw a vertical line where x equals 13. And notice if I zoom in here, it's extremely close. For my regression model, his height when he's 13 years old will be 166.895 centimeters. And for my linear model that I use by looking at just the first and last points of data, his height will be, what is the difference there? 0.1 centimeters. that's a millimeter. And so extremely close. And so I want to write those numbers down just to show how close these two models are. And I should get the exact same values if I just literally substitute x into my two equations. So I'll say for my regression model, we get his height to be about 167.03 centimeters. And for the point slope model, his height comes to be 166.8. Actually about 90 if I rounded to 2 decimals. So, you know, negligible difference considering we're making a prediction about a person's height at some point. I mean, that's a negligible difference, a millimeter. Lastly, though, then, according to these models, how tall was the boy when he was born? Well, I have two options. One is to look at my graph. And when according to these models, when he was born, let me zoom out here. I look at the y-intercept, right? That's when his age was 0. And for my regression model, he was about 81 centimeters tall. And for my point slope model, he was about 80 centimeters tall, a difference of about a centimeter. Now that's it. Hopefully you realize I didn't really need to look at this graph, because if I look back at here, especially if I look back at my regression equation, that's my y-intercept right there, which I could also find if I actually distribute 6.67 and collect like terms, I'll find the equivalent y-intercept for my point slope model. They're both around 80 centimeters. And so according to my model, this boy was about 80 centimeters tall when born. Let's pause and think about that for a moment. That's almost a meter. Now, a good sort of rule of thumb about what a meter is, you know, the height of a doorknob from the ground for a standard door is a meter. A little bit shy of that. That's a tall baby being born. So what that tells me is not that this boy was freakishly tall, is that this model, both these models, are they're definitely quite accurate models, at least looking within the data set we have. But clearly, as I get closer to birth, this model is no longer very accurate. No, you know, babies are not, you know, almost a meter in length when they're born. Thankfully so, for any females watching this video, you know, that so clearly this model is not appropriate as we get closer to birth. Somewhere in this region between this point and the y-intercept, this curve must, or this line must start to go down at a much steeper rate. But with the data we have, we just can't say for sure about where that is. Like I said, no model is perfect, just some are useful, and we have to know when they're useful as well. And I believe that's it, so I'm going to stop talking now.